Welcome to Tomorrow Unveiled. Over the past 7 days, well, the world of physical AI has really seen a seismic shift. It feels like we're witnessing a fundamental paradigm change. We seem to be moving decisively past that era where progress was, solely defined by new nuts and bolts.
Right. Hardware was king for so long.
Exactly. And instead, we've hit this critical inflection point. The focus seems to have completely pivoted to the platform. It's a software-defined, AI-driven revolution that's finally giving these complex machines the robust brains they need to function in our messy, unpredictable world.
It's about time the software caught up, really.
Our mission today on Tomorrow Unveiled is to guide you through the latest corroborated findings. We're zeroing in on three massive areas where things seem to be converging. First, the foundational software breakthroughs that promise, universal physical intelligence. Second, the tangible hardware demonstrations that prove this software actually works in the real world.
Yeah, seeing is believing with robots.
And third, the incredibly aggressive commercialization plans that tell us humanoids are no longer some, distant theoretical concept. They're basically arriving now. The humanoid form factor, the robot shaped like us, is kind of the ultimate testbed for general-purpose physical intelligence. And this week, it feels like several major players just cleared that bar almost simultaneously.
What's truly revolutionary here, based on what the research team that compiled this information concluded, is the shift in competitive strategy. It's not really about building the single best individual robot anymore.
Okay. So it's bigger than just one machine.
Absolutely. It's about establishing the dominant operating system, the whole AI stack, that's going to power all future robots, regardless of who actually builds the metal body. This period feels like the moment the AI brain hasn't just caught up to the complex hardware body, but maybe in many critical ways has actually surpassed it.
Wow.
Yeah, creating this blueprint for intelligent physical systems that's portable, versatile, and just immensely scalable. It's really an ecosystem battle now, not just a hardware showcase.
Right. So that ecosystem battle is playing out mainly in the software layer. And all the evidence seems to point towards this consensus architecture, the dual planner actor system.
Right.
This idea of separating high-level thought from low-level muscle control. It really looks like the dominant future design. But let's start with maybe the biggest bottleneck that had to be solved for any of this to even matter, the sim-to-real gap.
Ah, yes, the classic problem.
We've talked about this on Tomorrow Unveiled before, haven't we? Historically, when a robot skill like, say, learning how to grab a mug is perfected in a clean virtual simulation,
Looks great on screen.
it almost always fails, sometimes catastrophically, when you try it on the actual physical robot. The virtual physics just weren't accurate enough, right? Why is simulating the real world so darn hard for a computer?
Well, it really boils down to two things.
Mm-hmm.
Contact physics and computational speed. Simulating, say, two rigid billiard balls hitting each other. Relatively straightforward. But simulating the infinite subtle variables of the real world, like the exact friction when a robot hand grips a slightly sweaty glass, or the way snow compacts just so when a foot steps on it, or even the really delicate dynamics of handling a thin, deformable piece of cloth. That needs immense real-time computational power. These are what we call contact-rich dynamics, and mathematically, they're just kind of chaotic.
Gotcha.
So NVIDIA's strategic move, and this was confirmed by the research team, is basically to become the provider of the foundational infrastructure that solves this whole problem for everyone. Their solution is the Newton physics engine. It's GPU accelerated, and crucially, it was co-developed with giants like Google DeepMind.
Right, that partnership is interesting.
It is. By leveraging massive parallel processing on GPUs, the Newton engine can accurately and importantly rapidly model these complex contact-rich scenarios at scale. If you can simulate moving a fragile piece of fruit or the tricky dynamics of walking on, say, loose gravel with like 99.9% real-world accuracy.
That's really getting somewhere.
Exactly. You can train your AI robot thousands of times faster in simulation, and crucially, those skills will actually transfer when you deploy it in the factory or wherever. It's basically the essential bridge from virtual to real.
Okay, so the Newton engine makes sure the training environment is solid, it's accurate. Now let's look at the brain structure built on top of that foundation. That's NVIDIA's cognitive architecture, the dual brain system you called it.
That's right. The dual architecture is the functional core. It separates the cognitive load, making sure the robot's intention is distinct from its actual execution. So you have the planner. That's the NVIDIA Cosmos Reason model. It's essentially a massive vision language model, a VLM.
Okay, VLM, like the big AI models we hear about.
Precisely. Think of the VLM as the CEO. A human gives a high-level, maybe slightly vague command. Go clean the kitchen. The VLM takes that ambiguous goal and uses its vast language understanding and its visual context to break it down into a structured, sequential plan. Like, first, identify and collect the dirty dishes. Second, load the dishwasher. Third, wipe down the countertops, step by step.
Makes sense.
Then you have the actor. This is the Isaac GR00T N1.6 foundation model. This is a VLA, or Vision Language Action model.
VLA, so the A is for action.
Exactly. This is the executor, the doer. It takes the structured subtask from the planner, say, wipe down the countertops, and translates that intention into continuous, ultra-precise motor commands. We're talking about generating the exact joint angles, the precise torque requirements, the velocities needed for the physical body to actually do the wipe without, shattering a bottle or dropping the sponge. This split is what makes the system robust. If the actor fails a step, the planner can simply tell it, okay, try that again, or maybe generate a new, slightly different plan to get around the problem.
That's NVIDIA basically building this open, horizontal operating system for the world, it sounds like. But then Google DeepMind came out swinging with a powerful, tightly coupled, more agentic system. Their approach seems less about providing the underlying infrastructure and maybe more about providing the finished, highly integrated intelligence package. Is that fair?
That's a perfect way to frame the contrast, actually. Google's Gemini Robotics 1.5 is a really deep vertical approach. They're making the entire thinking robot brain available via an API. They're focusing hard on pure cognitive sophistication. The research team highlighted several conceptual advances, but perhaps the most, human-like one is this concept of thinking before acting.
I love that phrase. It sounds like the robot's having a little existential moment before it loads the dishwasher.
Precisely, but with a purpose. The system actually generates an internal monologue, like a detailed reasoning chain, in natural language before it commits to a physical action.
Really? Like it talks to itself?
Sort of, yeah. If it's asked to move a box, for instance, and realizes the path is blocked, its internal monologue might literally be something like, okay, path A is blocked by those unstable pallets. I calculate a 60% risk of collision if I proceed that way. I will generate path B through the left aisle instead.
Wow. Okay, why is that important for, for us, for the listener?
Well, two main reasons. First, it massively increases robustness because the robot can dynamically reason its way out of unexpected stuff. Obstacles, changes.
Right, it can adapt.
Exactly. And second, and this is crucial for human coworkers, it provides transparency. If the robot pauses or maybe fails at something, it can actually explain its decision-making process in plain language.
Yeah.
I stopped because that makes it far more trustworthy and way easier to debug or understand. It moves the robot from just a black box tool to more of a transparent colleague.
That transparency is key. But the truly critical breakthrough, the one that sounds like it could accelerate the entire industry, not just Google or NVIDIA, is this cross-embodiment learning. That sounds like pure science fiction.
It's pretty close. It really is the holy grail of physical AI. To understand why it's such a breakthrough, you have to appreciate how difficult this usually is. See, every robot body, every embodiment is different, right? A dual-armed LOA2 robot has totally different joint limits, torque specs, degrees of freedom than, say, a bipedal Apollo humanoid.
Okay, yeah. Different shapes, different capabilities.
So if you train a skill, like stirring a pot on Robot A, that skill is inherently tied to Robot A's specific body configuration. Historically, trying to transfer that skill to Robot B meant you had to retrain the model almost completely from scratch just to map the visual data to the new robot's movements, its kinematics.
Which takes a ton of time and data.
A huge amount. Cross-embodiment learning, and our research team confirmed this is working, allows the intent of the action, the core conceptual understanding of stirring, to be instantly transferred between completely different robot types without retraining.
Instantly, without retraining.
Pretty much instantly. It means a skill taught to some static lab arm could be used immediately by a walking, full-size humanoid in a different location. It makes the intelligence itself portable. That slashes the time and cost needed to teach new hardware, new skills. It effectively commoditizes the body in favor of the brain.
So what's the big picture here, then? We've got NVIDIA pushing the infrastructural side, the accuracy, the modularity, and Google pushing the cognitive smarts, the portability, but both seem to be converging on this planner actor design.
It really signals, I think, the end of the robotic Stone Age. The consensus seems to be that this dual architecture is the blueprint moving forward.
Hmm.
The competitive advantage is shifting pretty decisively away from just the hardware alone and toward two new battlegrounds.
Okay.
First, data generation. Who can feed their VLM the most varied and accurate physical world data? And second, just the raw sophistication of that planning VLM itself. The race is really on now to create the most insightful, general-purpose synthetic intelligence.
Okay, so these software leaps are fundamentally changing what these physical machines can actually do. We need to connect those powerful AI brains to the tangible brawn, right? The physical capabilities we saw demonstrated just this past week, focusing on dynamic stability and that skill transfer you mentioned. And there's one anecdote we absolutely have to start with: the Kung Fu robot.
Ah, yes, the Optimus demo.
Tesla Optimus demonstrated this really complex martial arts routine. We're talking side kicks, blocks, dynamic balance, flowing transitions, with a level of speed and fluidity that, honestly, it looked choreographed. It was pretty stunning.
Yeah, it was impressive. And the initial reaction from some people was, oh, that must be teleoperated. Someone remotely controlling it like a pivot.
Right, that was my first thought, too.
But the research confirmed this routine was fully autonomous AI-driven control. And that is monumental. It showcases a major leap in learned motor skills and real-time balance, which is fundamental if you want general-purpose utility. It's really a showcase of imitation learning working at scale.
So it learned by watching.
Essentially, yes. Think about what it takes for a robot to do a sidekick. It needs to observe a human video demo, translate that 2D visual information into a complex, continuous sequence of 3D motor commands, tailored precisely to its own joints, its own weight distribution.
All while staying balanced.
All while maintaining this state of dynamic, inherently unstable equilibrium. It's not relying on rigid, pre-programmed steps anymore. It's using a single, unified neural network, kind of like the new large behavior models we've seen in similar work from Boston Dynamics with Atlas, to govern both manipulation and locomotion together. That unified control is what allows that fluidity, letting the robot perform these complex, continuous sequences of tasks smoothly.
Beyond learning new tricks, though, for these things to be viable, they need resilience, right? A robot that falls over every time it hits a bump isn't a coworker, it's a liability.
Exactly.
We saw this principle really emphasized in the Unitree G1 humanoid demo, showcasing what they called anti-gravity mode.
Yeah, that G1 demonstration was pretty brutal as a stress test. You saw the robot withstanding powerful kicks, big lateral pushes, shoves from multiple angles.
Looked like they were really trying to knock it over.
They were, yet it recovered its balance almost instantaneously. It wasn't just standing still either. It was dynamically adjusting its posture while under attack. It proved it could be, take a hit and keep working.
How is that speed of correction even achieved? What's the engineering trick behind that?
Well, it's a combination of lightning-fast perception and really high torque execution. The robot uses this tightly integrated sensor motor control loop. Its eyes, the depth cameras, the 3D LiDAR, are constantly fusing data in real time, predicting exactly where the force is coming from, and calculating precisely the shift needed in its center of gravity to counteract that disturbance.
In milliseconds?
In milliseconds, yes. That prediction then gets fed to high-torque motors, which can execute these rapid corrective posture changes instantly. If that whole loop takes too long, even by a fraction of a second, the robot falls. It's that critical. So for humanoids to be trusted coworkers in, say, an unpredictable factory, or eventually maybe even a home environment, this kind of non-fragile nature has to be the new baseline. It reduces insurance risk, it increases uptime, and crucially, it builds essential public trust in their reliability. I mean, nobody wants to hire an assistant that breaks if you accidentally bump into it, right?
Definitely not. Yet despite this really impressive progress on dynamic bipedalism, the research team noted an interesting split happening in the market in the hardware itself. We're seeing this bifurcation between the really ambitious bipedal generalists like Optimus and maybe more pragmatic wheeled options focused on immediate profit.
Yeah, this is where practicality kind of hits ambition head on. The emergence of that UK startup, Humanoid, and their HMND01 alpha model. It's a perfect case study in prioritizing near-term ROI, return on investment. This is a robust machine, a dual-armed mobile manipulator. It stands 220 centimeters tall, can carry a decent 15-kilogram payload. But, and this is the key part, it deliberately uses a wheeled base.
Ah, okay. So they sacrifice the ability to climb stairs or handle really unstructured terrain, but they gain immediate stability and probably lower costs. Seems like a smart trade-off to get the product out the door faster.
It absolutely is a smart strategy for market penetration right now. Our compiled research noted their remarkable development time, just 7 months, which is incredibly fast.
7 months.
And that's a direct reflection of leveraging that standardized AI platform stack we just talked about. They didn't have to reinvent the wheel, or rather, the brain. They're focused hard on a robots as a service model, RaaS, targeting the immediate massive labor shortage in structured places like distribution centers, logistics hubs. By avoiding the engineering nightmare of high-speed bipedal walking, they lower the risk, they lower the cost, and they become viable for industrial deployment years faster than their bipedal competitors probably will be.
And that commercial viability is being backed up by financial numbers that are, frankly, a little hard to comprehend sometimes. The research team confirmed this massive, unprecedented flow of capital into the sector. It really signals this isn't a science project anymore. It feels like a full-scale industrial race.
The money is definitely flowing.
I mean, the numbers tell the story. Figure AI recently surpassed $1 billion in committed capital in its latest funding round. $1 billion, and that gave it an eye-watering post-money valuation of $39 billion.
$39 billion, that's huge.
That's the kind of money you historically only saw in like the most disruptive software or internet sectors. And it's not isolated either. UB Tech, the Chinese developer, also secured a massive $1 billion credit line. That money has to be flowing because these companies have really aggressive, concrete deployment plans, right?
Absolutely. And when you talk about aggressive, you really have to look at Tesla's scaling projections. They seem to be moving from prototype to production at a velocity that kind of echoes their early days in EV manufacturing. Their internal goal, reportedly, is to deploy 5,000 Optimus units in 2025.
5,000 units next year. That alone is an insane operational challenge. And that number isn't about selling to external customers yet, is it? That's about solving Tesla's internal labor needs first.
Exactly right. They're using their own vast factory ecosystem as the ultimate test bed and, initially, their own primary customer base. Deploying 5,000 complex machines like this requires a massive industrial scaling effort. You got to ramp up the supply chain for all those specialized actuators, integrate manufacturing quality control, develop internal training, maintenance protocols. It really demonstrates absolute corporate commitment from the top down.
And it's not just Tesla pushing hard.
No, we're seeing parallel success elsewhere. Figure AI's partnership with BMW, for example, seems to be already past the initial pilot phase. Our research confirms that Figure 02 robots have actually been performing autonomous industrial tasks at the Spartanburg plant since January 2025.
Already working since January.
Since January. This shows that transition from a lab demo to a functioning industrial coworker isn't some future projection. It's happening right now. It's a present reality.
And the potentially high cost of this cutting-edge hardware that's being managed through the RaaS model you mentioned earlier, robots as a service.
Yeah, that's becoming really common. The initial capital expenditure for a single sophisticated humanoid is still very high. We're likely talking well into the six-figure range per unit. Yeah. So, to lower that barrier for adoption, the industry is widely embracing robots as a service. Instead of buying the robot outright, companies essentially subscribe, paying an hourly or monthly fee. This shifts the big financial risk and the ongoing maintenance burden onto the manufacturer, which makes deployment economically feasible much sooner for, the average customer who just needs immediate labor relief in their warehouse or factory.
Makes a lot of sense. Okay, before we move on to the reality check section, we do need to take just a quick moment to ask you, our audience, to participate a little. If you're finding this insightful, maybe learning something new, please take just a second to like this video. If you're on YouTube, subscribe to Tomorrow Unveiled, and maybe consider hitting that new hype button. It really helps us reach more viewers. And of course, make sure you turn on notifications so you never miss an update on the future.
And if you're listening on a podcast service, maybe Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and perhaps a review for Tomorrow Unveiled. It truly does help us reach new listeners, and honestly, it helps fund the deep analysis we try to bring you every week.
Okay, thanks everyone. Now let's bring some necessary context to all this excitement. A key question arises. Why does the general purpose humanoid really matter when we already have specialized, highly optimized robots doing specific tasks really well? We saw the launch of the DoorDash delivery robot just this week. Why not just build more and more highly focused specialists like that?
Yeah, that comparison between the specialist and the generalist is absolutely fundamental to understanding the future market, I think. The DoorDash Dot is the perfect example of purpose-built efficiency. It's a wheeled robot, definitely not humanoid, designed purely for one single task. Suburban last-mile delivery. Can travel at 20 miles per hour, carry 30 pounds. It's highly, highly optimized for its single-domain driving on sidewalks and streets.
Right. And its a big limitation is its inflexibility, isn't it?
Yeah.
It's basically a very smart, fast box on wheels.
Exactly. The dot just cannot handle the complexity of the human environment. It can't climb the steps to an old brownstone apartment, it can't open the customer's front door, and it certainly can't navigate the cluttered interior of your kitchen to put the groceries away. The humanoid's immense value lies precisely in its generality. Its bipedal form, its dexterous hands allow it to climb stairs, operate tools designed for humans, and adapt to the infinite variety of tasks in all sorts of unstructured environments. This generality represents a far, far larger potential future market than any single specialized robot could ever address.
So the specialists prove the tech works, but the humanoids unlock the bigger potential.
That's the key synthesis, according to the research, yes. The commercial success of specialized robots like the DoorDash Dot, it validates the underlying autonomy stack, the navigation, the planning software, the perception systems, but it also reinforces the truth that the generalist humanoid is absolutely required for, say, the 80% of complex physical tasks that specialists are just structurally incapable of handling.
Right. So to maintain that balanced view that Tomorrow Unveiled is known for, we have to look past the cool demos and the huge evaluations at the hard reality that still remains. The research team identified 3 universally cited technical hurdles that really must be overcome for scaling these machines from, thousands of units to potentially millions. These seem to be the consensus challenges separating the prototype from true ubiquitous utility.
Yeah, these are definitely 3 major roadblocks, and they are intensely challenging engineering problems. The first one, and arguably the most paramount for continuous industrial operation, is battery life.
Still battery life.
Still battery life. Current prototypes, as impressive as they are dynamically, offer only about 3 to 4 hours of runtime before needing a pretty lengthy recharge. That's just entirely insufficient for a full factory shift, or really any meaningful continuous work.
Why is it still so hard? We've had lithium-ion for ages.
Well, bipedal locomotion, that dynamic balance, the high torque movements needed just to keep a human-sized machine upright and active, it consumes an enormous amount of power. The power density required in those battery packs is really pushing the absolute limits of current lithium-ion technology. The industry is urgently looking at next-gen solutions, things like solid-state batteries maybe, or perhaps more pragmatically, relying on fast, swappable battery packs to allow something closer to 24/7 operation. But this remains arguably the single biggest operational barrier to widespread industrial adoption right now.
Okay, number 1 is power. What's the second challenge? It focuses more on interaction, right? Dexterity. We see them doing martial arts, which is cool. But can they truly manipulate the world with the finesse of a human hand?
Not yet. Not really. True human-level hand dexterity, the ability to handle fragile, varied objects, feel subtle textures, apply really precise modulated force, that's still largely an unsolved problem. It requires a rich, robust sense of touch, something far more complex than just vision. Current robot hands, or end effectors as they're called, they generally lack the high-resolution tactile sensors and the subtle actuation needed to handle something like, say, wet pasta or a single thin sheet of paper without tearing it or crushing it.
Right, the fine motor skills.
Exactly. This is a massive area of ongoing academic and corporate research focus because true general-purpose utility absolutely demands those fine motor skills. And then finally, the third challenge is simply cost and supply chain. It's the economics. The high-performance hardware, we're talking precision actuators, advanced sensors like LiDAR, the specialized onboard computers needed to run these huge VLA models in real time, it's all extremely expensive right now. Plus, the specialized component supply chains just aren't robust enough yet to handle mass production rates of tens or hundreds of thousands of units per year. That's going to create bottlenecks and likely keep the unit cost prohibitively high for most consumers and even many businesses for the foreseeable future.
So power, hands, and money. If those technical hurdles weren't enough, we also have to address the immediate threat of, well, physical cybersecurity. Because when a machine can walk around and manipulate the world, a software vulnerability suddenly becomes a profound physical danger.
This is critical.
The specific threat here, confirmed by our research, is the publicly disclosed Unipune cybersecurity vulnerability. It apparently affects Unitree robots and other similar quadruped and humanoid robots running certain control systems.
Yeah, and this is a really stark warning for the entire industry. The Unipune vulnerability essentially allowed an external attacker to gain root control wirelessly over the robot.
Root control? That sounds bad.
It is. We have to emphasize what root control means in a physical context.
Yeah.
It means the attacker can override all commands, all safety settings, all movement parameters. A compromised robot isn't just a data breach risk anymore. It transforms into an immediate, tangible, physical danger.
Wow.
Look, the threat of a robot botnet, a sort of decentralized network of compromised machines that could be controlled maliciously to cause physical disruption or damage, is very real. This threat just heightens the immediate and critical need for secure, encrypted communication protocols and incredibly robust, independent physical fail-safe mechanisms, things that can cut all motor power even if the main control computer has been completely hacked. Safety cannot be an afterthought here. It has to be absolutely central to the design from day one.
And this proximity to actual deployment, it's finally forcing standards, bodies, and regulators to take humanoids seriously, isn't it? It's not abstract policy anymore. It's about safety on the factory floor potentially next year.
Absolutely. The regulatory environment really has to play catch-up with the technology now. The IE Humanoid Study Group, for instance, has published a new framework precisely because existing industrial safety standards, which were mostly written for fixed robotic arms bolted to the floor or maybe slower automated guided vehicles, they simply did not account for bipedal, human-sized machines operating dynamically right alongside people. I mean, a machine that is inherently unstable by design, just to be able to walk, requires entirely new rules and metrics.
So what are they calling for?
Well, the new framework calls for specific new metrics for several critical areas. First, stability and fall risk. You need ways to quantify a robot's balance in real time and, importantly, define safe fall behaviors. How should it collapse to minimize risk to nearby humans and damage to itself?
Okay, it makes sense.
Second, human-robot interaction. Ensuring these humanoids operate in ways that are trustworthy, transparent, and physically predictable when they're working shoulder to shoulder with human coworkers. The research group's ultimate goal seems clear. Widespread adoption is going to depend just as much on shared, standardized safety protocols and clear liability frameworks as it does on the next technical breakthrough. I mean, no major company is going to deploy 5,000 of these things without solid confidence in the safety standards. So as we kind of look back on the whirlwind of progress just in the last 7 days, the central takeaway for Tomorrow Unveiled listeners is probably this. The AI capabilities, the sophisticated reasoning, the reliable planning, that portable cross-embodiment learning, they are advancing at just breakneck speed. This progress has really laid the necessary, robust software foundation. The hardware, while impressive, is now arguably the lagging component. The focus is shifting almost entirely, it seems, to hardening that physical layer, extending battery life to a full shift, achieving true human-level dexterity, ensuring rock-solid physical security against wireless attack, and critically scaling up that component supply chain.
And this momentum points directly toward what the research team's analysis called the Android moment analogy, which I think is quite powerful. Think back to the early days of smartphones, right? Apple created the iPhone, proved the concept of a modern mobile OS fantastic device.
Game changer.
Then Google released Android. They created a common, powerful software platform that effectively democratized smartphone intelligence. When that common, accessible platform arrived, it basically commoditized the phone's brain. And that sparked an absolute explosion of competitive innovation in the hardware, the phone bodies themselves, dramatically lowering the barrier to entry for smaller manufacturers all over the world. We seem to be seeing that precise transition happening right now in robotics. The creation of a universal, powerful AI stack, whether it ends up being dominated by the NVIDIA platform or the Google stack or something else, it will likely commoditize the robot's intelligence, which means the next generation of competitive breakthroughs will probably come from cheaper, faster, or maybe more specialized hardware bodies, all built atop that shared software foundation. We're transitioning from the era of proprietary, isolated robotic systems to the era of the universal general-purpose platform, really getting ready for mass adoption.
And, as we move toward this world where humanoids could become ubiquitous, stepping onto our factory floors, maybe into our homes, certainly into our public spaces, the core question really starts to shift. It moves from a purely technical one, can they do the job, to a deeper, more sociological and maybe even psychological one. How will they change our human identity and our very definition of work? End quote. The biggest challenge ahead might not actually be a lack of battery power or more dexterous hands. It might be the ethical and sociological integration of machines that are designed deliberately to look and move like us, occupying these inherently human-centric spaces. That integration, that's the frontier we really need to watch closely now.
A really provocative thought to end on. We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, please leave a comment and let us know what you think about the rise of these thinking machines, and maybe how quickly you think they're moving from the lab into the real world. We'll definitely be tracking their journey right here on Tomorrow Unveiled. Thanks for diving deep with us.